Hello, welcome back to AP Physics 1. Today's PowerPoint that we're going to be going through is on motion. And I started off with kind of a silly slide here, count the dots. So what we're going to be doing, focusing on today, is motion in one dimension, so either in the x direction or the y direction. There's two main types of motion. There is linear motion, which is translating. There we go. There's translation. Okay, which is moving around in a line, okay, moving along a curved or straight line path, or rotating. Today we're focusing on translation. Later on we'll look at rotation. But a quick question to start out: how can you tell if something is in motion? Most of you would say that, well, it's changing position, its location is changing. And then the next question is, how can you tell if something is changing position? Well, in order to do that, you need to see if it's moving compared to something else. For example, if I were to ask you if your Chromebook was moving, you would probably say no, but it depends on how you thought about it. My desk, which is currently, I don't even know where my teacher desk is now. So there's me and my teacher desk on the earth, and most of you would probably have said that my desk was stationary, but it was stationary compared to the surface of the earth. However, the entire surface of the earth is rotating, so you can't totally say that the desk is stationary. And you can certainly make an argument that it's definitely not stationary. Not only that, but the whole earth is rotating, or sorry, is revolving around the sun. And not only that, the earth is rotating and revolving as it goes around the sun at the same time. And the solar system is just a little speck in the Milky Way galaxy, and the arms were in one of the arms of this galaxy, and the whole galaxy is spinning. So whether or not my desk is moving, it definitely is moving. It definitely is moving. In order to judge whether or not something is moving, though, we always compare it to something else. Okay? And you can't necessarily really say if something is moving or not. You have to say if it's moving compared to something else. So, for example, is the car moving? You would say yes, it's moving. And what we would understand there is that it's moving relative to the road, relative to the speed limit sign. You always do this. If you're trying to figure out if something is moving, you always compare it to something else. For example, if you've ever had this experience where you're at a stoplight or a stop sign, especially on a hill, and let's say that the person next to you lets off their brakes, and they start to move, whereas your foot's still on your brake, you might assume that you're moving because they're moving. You're comparing your motion to them. And it might freak you out, make you think that your brakes failed. But anyway, we always judge motion relative to something else. If you were in a spaceship in outer space, and there was no stars and nothing around for you to look at, could you devise an experiment to see if you were in motion at a constant speed, or whether or not you were moving, or if you were stationary? Their answer is you really couldn't. There's no experiment you could use to determine whether or not you were moving or stationary if you were moving at a constant speed in a straight line. Now, if you were accelerating, you could definitely determine whether or not you were accelerating. You could use a simple glass of water, and the liquid level in the water would shift in the direction, or opposite the direction, that you were accelerating. So again, motion is always judged relative to something else. So we'll talk about relative speed, the speed compared between two objects. For example, here we've got a train, and the train is moving at 50 meters per second relative to the ground. We've got a stationary, quote unquote, stationary observer. We have a person who is on the train and is simply standing. A person that's walking to the front of the train at 3 meters per second, person C, and person D, who is walking backwards at 5 meters per second. And we want to figure out the relative speed between each of these people. So if we want to figure out the relative speed between person A and person B, okay, that would be 50 meters per second. If we wanted to figure out the relative speed between person B and person C, it would be 3 meters per second because they're both on the train moving at 50 meters per second. And anyway, and then if we look at the relative speed between person A and person C, that is going to be 53 meters per second because he's moving with the train and those velocities are adding. If we look at the relative speed between person A and person D, okay, this person is walking backwards on the train against the 50 meters per second, so their relative speed is going to be 45 meters per second. Between person B and person D, it's just going to be 5 meters per second. And between person C and person D, that is going to be, which is it going to be? Think about it. Is it going to be 2 or is it going to be 8? And it's going to be 8 because they're moving towards each other, so those velocities add up. When we describe motion, we'll use words, we'll use pictures a little bit. We will definitely be using a lot of equations as well as some graphs. Motion can be simple or complex. So here we've got kind of a stroboscopic image of a girl. I don't know what she's doing. It looks like she's doing like a flip or something like that. So when we go to describe motion, we're gonna need to talk about things like its speed, how fast is it moving. We'll need to talk about the direction, which way it's going. We will need to address whether or not it's moving at a constant speed, whether it's speeding up or slowing down. So, and also whether or not it's traveling in a straight line path or turning. In the beginning, we're going to be simply looking at translation, which means moving through space and time as a whole in one dimension. So in a straight line path at a constant speed will be what we start with. Now, when we go to analyze, we're going to want motion. We're going to definitely be using a lot of math. And in order to do that, we need to superimpose a Cartesian coordinate system on the universe. And this is pretty simple. Really, for most intents and purposes, it's going to be sticking a person on a number line. So here we've got a runner on a number line. So now we can determine where they're at a specific moment in time. The first definition that we're going to look at here is displacement, which is basically how far and which way an object ends up from where it started. Okay, so displacement is how far and which way an object ends up from where it started. Mathematically, we're going to write this as delta x or delta y. The delta means change in. Okay, so delta x or delta y. That's what the triangle is, obviously delta. Now, how you calculate this, how you calculate delta x, is just x2 minus x1, similar to when you're finding the slope of a line. So delta x, which is the displacement in the x direction, is going to be the x2 minus x1. So here we've got, and the x2 means the final position, and x1 means the initial position. So that should make pretty much sense. So to figure out the x2 minus x1, it looks like the final position was about, where did we start from? The back was lined up. So 28 meters approximately minus 0 meters. So the displacement was 28 minus 0, or about 28 meters. Okay, so again, using the formula, x1 means the initial position, x2 means the final position, and the displacement is x2 minus x1, so it's going to be 40 minus 0 would be 40 meters. Now, some other notation that you might see, instead of using x1 for initial, you might see xi for initial and xf for final position instead of x2. Hopefully that won't throw you for a loop. Another commonly used form is x for the final and then x naught, meaning x at time 0. You might see this is actually the way that the equation sheet uses their equations. I just prefer to use x1 and x2. You know, that's just what I prefer to use, so I stick with it. You'll get used to seeing these different forms though. So displacement. So here we've got we're starting at the 40 meters, so that's my x1, and then my final is x2, which is 0. So if I figure out the displacement, it's going to be 40 meters, but the question is it going to be positive or negative? Well, if it's final 0 minus initial 40, it's going to be negative 40. And what would the negative mean? Okay, what do you think? Well, the negative means that you ended up traveling to the left. So the negative is the direction, and you'll see that very, very commonly in physics. The sign of a number is used to specify the direction. So very commonly we have the left is the negative x direction, and very commonly we have positive x to the right. You'll see that very commonly. If we practice this a couple more times and look at it, x2 minus x1. So here's my final is at 50, and my 80 meters is my initial. So 50 minus 30, or 50 minus 80 is negative 30 meters. So that negative means that I moved to the left. So remember, displacement means basically how far and which way an object ends up from where it started, and ended up 30 meters. Okay, and the which way is that negative. Okay. Very commonly we use positive x to the right, negative x to the left, positive y up, and positive or negative y down. You don't have to stick with these though. You can choose whatever system. If you want to call to the right negative and to the left positive, you can do that as long as you're consistent. That's all that really matters. And there are definitely times when we'll consider down to be positive instead of a negative y direction. If an object is falling downward, we're more than likely to just consider down to be positive. So here we've got a skydiver, and we put a number line on him, and we can see that the downward direction is positive here. So any positive number would mean that he fell down. So here we've got just another example or two. We've got a final position of 30 and initial position of 0. So final minus initial, 30 minus 0 gives me positive 30 meters. So you travel 30 meters and then to the right, in this case, plus x is to the right. If I flip this system and now I have positive moving to the left, okay, and he ends up moving to the right, well, that's going to end up with a negative number because I've said left is negative, so right is positive. Or right is, I said left is positive, excuse me. So right is negative. So when I find my answer here, 20 minus 50, that's going to be minus 30, and that negative 30 is going to mean that he traveled to the right, because I've said to the left is positive. So we can also move upwards and downwards. So here's my Cartesian system. Here I went ahead and said that down is negative and up is positive. Increasing numbers and positive would of course mean that that's the positive direction. So if we start at the 30 and move to the minus 10, well, that's going to be minus 10 minus 30, okay, because we're subtracting the negative 30, which was our initial position. So that's going to end up with a positive number. So we ended up moving upwards to the right, and upwards to which is positive. I think the displacement we've talked quite a bit about. There's a related but different quantity called distance, one that we're quite familiar with. Displacement is how far and which way we end up from where we started, and distance is the total length of the path traveled. So these are different quantities. So if we were to look at the displacement of this person who follows this path, okay, anyway, if they don't move along there, the displacement, if they follow this path, is the blue line. How far and where they ended up, how far and which way they ended up from where they started. The distance would be the total length of this path as if I stretched it out. Okay, so displacement would be the blue line, the blue arrow, and the distance would be the length of this line stretched out. So if we go to Walmart or Sprawmart, sorry, I can't advertise, and we take a round trip and our speedometer reads 5.2 miles more than when it started, if we figure out the distance and the displacement, the distance is going to be the 5.2 miles that they travel around, okay, and the displacement is actually going to be 0 because they end up back where they started. So since they end up 0 meters away from where they started, the displacement is going to be 0. I think that'll